Okay, I'm starting the thing. Okay. Hello and welcome to another wonderful episode of the New York City Category Theory Seminar. Today we have Grigorios Giotopoulos, who's speaking to us from Abu Dhabi. So that's interesting. And he's going to talk about thickened smooth sets, natural settings for Lagrangian field theory. Take it away, Grigorios.
Dude, thank you very much for the invitation and for waking up so early there to
Oh,
listen to
it's
me
10
talk.
o'clock. That's not terrible. Okay, good.
So yeah, my name is Grigorios Giotopoulos. In Greek, it's Grigorios Giotopoulos. So I grew up in Athens until I was 18. Then I left. I went to Edinburgh University for my undergraduate. And following that, I did my master's in Cambridge and then went back to Edinburgh City in Scotland, but at Heriot-Watt University to do my PhD. Yes.
Go.
Right, and today I'm going to talk to you about basically mathematical foundations for physics, for field theory. So,
Good. Can I make it a little? Can you make it a little louder?
can I make it a little louder? I can speak louder. Does that work?
Yeah, that works.
Okay, I'll
Okay.
do that. Very good. Or maybe I've done this wrong. How about now? Is the sound better?
A little better, but your screen. Okay, good.
Yeah, it should be fine. Okay.
Yeah, good.
Very good. Okay. Yeah, so I'm going to talk about mathematical foundations for mathematical physics, basically. So this is going to be something in between maths and physics. So it's not going to be fully categorical, internal in any categories I mentioned. But the reason being is that we want to make contact with traditional physics, the way it's written. So, and we're trying to play both ways. Of course, for some mathematicians, it's going to be a bit unpleasing, but and similarly for some physicists. But for the people we want to head for, I think this is the right way to do it. So anyways, so I'm going to talk about what we call thick and smooth sets. So this is a particular category, category of sheaves, which is a well-adapted model for synthetic differential geometry. And the point being is that it's a simple one. The site of probes, as we call them, where the sheaves are defined over, they're simple objects which we can think of intuitively and which do appear in physical manipulations, calculations, and textbooks. So that's the reason being for focusing in such a simple category for synthetic differential geometry. And the second reason is that then not being fully internal by working what we call plotwise or level-wise, maybe it's called in some texts, then you can make a direct contact with physics. Anyways, so this is, we advocate, this is a natural setting for classical Lagrangian field theory. Let me just say this is based on the paper that's already out. This is a field theory via higher geometry, part 1. This is just smooth sets of fields. You see, I've omitted the thickened here because there is no infinitesimal structure in there. But still, even with just smoothness, you can do most of physics. Textbook field theoretical classical physics. You can formulate that way. It's just that some constructions are not natural from the categorical point of view. You have to be a bit heuristic about it. And the second part of this series is going to make these heuristics rigorous. And so it's going to come out soon. The first one is published just this week, actually, after a year of reviewing, because it's big. It's 120 pages. And this one will be shorter, and it's going to make these ad hoc sort of heuristic arguments and maybe definitions fully rigorous, and they come from a categorical point of view. Okay, I should say this is a joint work with Hisham Sati and Urs Schreiber, from whom I've learned a lot of this material since coming to New York University, Abu Dhabi, here for my postdoc. Okay, so let's start with the plan of the talk. By the way, please feel free to interrupt me. I understand most people are mathematicians here and have a categorical background. So if anything in the physics description is too new, just interrupt me and I'll try to make it more precise maybe. Or give an
Are
example.
you saying in the first paper that you're not using any infinitesimals, but in the second one you're going to? Is that right?
Yeah, so in the first, so I'll explain how that works. I'll start again in this talk. I'll start with just smooth sets, and there are some things that you can formulate there rigorously, like the variational principle and so on, or jet bundles. But they have to be sort of, some notions are important, as in fully faithfully embedding first from manifolds, then taking limits and so on, rather than doing something directly in the category of these nice spaces. And furthermore, tangent bundles are not too natural in that setting. You have to sort of, for infinite dimensional spaces, you have to motivate them by taking equivalency classes of curves. So this works for what we call off-shelf full field spaces, but it doesn't work for intersections properly. So for critical loci. So that's a reason. So yeah, anyways, so to get ahead, the point is that for intersections, you have to sort of ad hoc define the what would be the tangent bundle on the critical locus in the smooth set picture, but in the thickened smooth sets using infinitesimals, it's a natural construction and it works by properties of pullbacks and internal home and so on. Anyways, let me just go with the plan, and please continue to interrupt me, of course. So I'll start off with a textbook sort of variational description of classical field theory, meaning it's not rigorous, and that's what we're trying to do is make it fully rigorous with the least amount of mathematical machinery that we can use, i.e. without using infinite dimensional manifolds and things that are unnecessary from the point of view of physics for most aspects. So after this discussion, I'm going to collect a list of desired properties for an ambient category where this description should be taking place in or seems to be taking place in. I will then recall briefly the definition of smooth sets and then thickened smooth sets and show how this sheaf topos, as it's called, satisfies these properties that we listed here. Onwards, I will give you a list of field theoretic concepts that you might have heard by words. I will not explain how they're all formalized, but I will tell you that now they are rigorously formalized in this setting. And not only are they rigorously formalized, in a way that you recover formulas from the physics literature. So it's not just abstract arrows in a category, but if you work carefully enough, with enough patience, you get out the formulas that the physicists write out in local coordinates for infinite dimensional spaces and so on. Time permitting, which might not be of interest for this audience, I was gonna talk more focus about what's called the covariant phase space, but that might be too much physics. So that's what people call this. So the fields that solve the classical field equations, if they come from a Lagrangian description, they are supplied with a presymplectic structure. So the space of fields in this kind of manner, in this thickened smooth set kind of sense, it has an extra structure which naturally comes from the Lagrangian. It's a presymplectic structure. All of this has been noted before in a loose sense by Fried, Zuckerman, and these people. Not loose, I mean, they know what they're doing, but it wasn't formalized in a rigorous setting. But here we can fully formalize it. Okay, so let me start with this part one, this textbook variational description of classical field theory. This is stuff people probably have seen before, at least once. So let's see. How does one define a classical field theory? What does one study at first glance? So you start with the kinematics, what we call the kinematics of the theory. So you fix some background space-time manifold, finite dimensional manifold, maybe with orientation and so on. Let's not worry about it. Maybe compact or not, which we call the space-time, and there is a field bundle over it in general, which dictates the nature of what the fields, the internal structure of the fields. As a definition, what physicists call the off-shell, i.e. not satisfying any field equations, space of fields, they say space, but it's really just a set. It's just a set of sections of some field, some fiber bundle, smooth fiber bundle over the space-time. For instance, if you take the field bundle to be just a trivial line bundle over space-time, then the sections of it become smooth functions, and this describes the off-shell space of set of fields of scalar field theory, what people call scalars. They're valued in the real numbers, just functions. If you take this to the cotangent bundle instead, this fiber bundle over M, then sections of it are just one forms. These describe, at least in the trivial topological sector, the gauge potentials for electromagnetism. So such a one form fully encodes globally defined electromagnetic gauge potential, but not in non-trivial topological sectors, and that's outside the realm of this. This goes on with part 3 of the series, but let's not worry about it. Okay, the dynamics of the theory then are dictated by some Lagrangian density, which is supposed to be a smooth map of some sort, which takes fields and it maps them to a top form, or pseudo form if you don't have any orientation and so on. So a top form on spacetime, which you can then integrate. I compose with the integration map, putting aside compactness and so on. You compose, and then this integration map should also be smooth, such that the integration is smooth in a sense, or people act as if it were.
And do you want to eventually make these maps of sheaves, right?
Yes. In the end, of course, yes. But now they're just set theoretic maps. The point is, in the end, defining your category and showing that these set theoretic maps canonically sort of extend. They define, you define the field space, you define all the spaces as sheaves over some site, and then you canonically sort of declare how these maps extend to maps of sheaves, right? That's the point. Yeah, of course. The Lagrangian is called local in the physics literature if it smoothly factors through the infinite jet bundle. So you have finite jet bundles. If people have not heard about this, I can make a remark, but probably, at least loosely, jet bundles are made by collecting all possible derivatives of sections at each point, point-wise. So this defines a bundle at any order k, and then you should take a limit in some sense, and that gives the infinite jet bundle. For physical reasons, you don't want to restrict to a specific order, so you need this infinity there. So anyways, so a Lagrangian is called local if it factors through the jet bundle in the following sense. You take your fields, which are sections of the original bundle F, then you prolongate them. There is a canonical set theoretic jet prolongation map that takes values in sections of the infinite jet bundle, and then you compose by some bundle map. So this is just a bundle map of over M of the infinite jet bundle into the bundle of top exterior power of the cotangent bundle. Okay, so this is the formula that's usually given.
Sorry, this is probably a dumb question, but I've been trying to understand. I want to think about this. Like, so if I take a smooth map and I take its like Taylor series, that's an element of the infinite jet bundle, right? Like the full Taylor series.
Yeah. So if you take, it's an element of the So if you take the Taylor series at a point of a function, that defines an element of the fiber over that point of this bundle. Right?
But it's not the case that every smooth map is exactly its Taylor series. Is that right?
Correct.
Right?
Exactly.
Because otherwise it would be analytic. So it's saying basically take like an analytic approximation to the smooth map.
Correct. Yeah. But because we only care about maps that come from actual sections of the original bundle, we don't care about general sections really. We only care about the image of this guy. The point is that then the Lagrangian is really given by such a composition. Okay, you don't really care about what it does in sections that are not jet prolongations of fields.
Right.
It doesn't matter. Yeah.
Gotcha.
You're right.
Thank you.
No worries. Yeah. Okay. So in this setup, we say a field configuration. Does this work? Yeah. A field configuration phi is called on shell. That's physics lingo. If it is a critical point of this action function, i.e., if you want to make it slightly more rigorous, if the derivative along any smooth one-parameter family of fields, whatever that means, that passes through that point at t equals 0 is 0, right? So this is the standard definition from classical differential geometry, if you want, or one equivalent definition of what a critical point is. And that's what is being applied in the infinite dimensional setting, but without declaring what we mean by all this smoothness and so on. Okay, so that's one part that we want to make rigorous. What does this mean? Why is it a smooth curve? In which sense? And is this the derivative, the normal derivative, or which derivative is it? Okay. So in the formal manipulation of Lagrangian field theory, if the Lagrangian is local, then you do some integration by parts manipulation, and you end up with such a form of the derivative of the action function being an integral over some pairing, where on this side you have the famous Euler-Lagrange operator. It's a differential operator, which comes out by integrating by parts. And on this side, you just have the derivative at t equals 0 of this smooth family of fields, which motivates the definition, if you want, from this point of view, that this would be a tangent vector right, at the origin of this curve. And if you look at the maths, this is an element in this pairing. This is an element of what? Well, the original phi is an element of sections of f, but this derivative along a smooth curve is an element of sections of the vertical fiber bundle over f over m. Okay, it's just taking the vertical fibers, the vertical subspaces of the tangent space of f. Okay, what does it say? The point is that this pairing is non-degenerate after integrating. So that means that if you demand that this vanishes for all such curves, then this is zero if and only if the Lagrange operator on the field phi is zero, meaning it gives you the zero section of the image that it takes into. So that rigorously, it's an operator. It takes sections of some bundle to some other bundle. This is what comes in this case. And if you just stare at these two bundles, this dual vertical fiber bundle pairs with this one, so with the tangent vector, and then what remains is a top form, which you can integrate over. So this formula makes sense if you want at the first glance. Anyhow, the point is that for local Lagrangians, criticality is equivalent to the vanishing of the early Lagrange operator. So this says equivalently in set theoretic terms at this point, it says that the critical locus of a local action functional made up of a local Lagrangian is equivalent, canonical bijection with a set of fields that vanish under the Euler-Lagrange operator. In other words, if you want, more categorically, in sets, it says that, well, the critical locus is a pullback of this, in the diagram of this form, is the zero section of some bundle now, infinite dimensional, no smooth structure yet, we're just talking about sets, some bundle over our space of fields, which we call the variational cotangent bundle. So it's a form of a cotangent bundle, but for tangent vectors on a field space. And it comes from the variational principle. So this is the bundle, if you want. You see, I'm viewing now. One has to take a step further. I'm viewing sections of a bundle as a bundle over another section of a bundle. Okay, I mean this makes sense. It's just you have to just forget about it. But it's said theoretically, it's a bundle over this. So you have the zero section of it. It's a vector bundle over it. So you have the zero section, and then you have the Lagrange operator, which is another section of this bundle. And then you can take the critical locus, the sort of vanishing locus, the pullback of this diagram. So this is a description that comes out if you just stare at the textbooks from theoretical physics, but without picking at the details of what you actually mean by smoothness and so on. So let's see now, from this picture, what do we extract that we need for a notion of a generalized, a category of generalized smooth spaces that should incorporate all these words that I mentioned, infinite dimensional spaces and smoothness and so on. Smooth paths and in field spaces, tangent bundles to them, and so on. Right, so what do we want from this category? First of all, we want mapping spaces, such as, let's say, also sections of bundles. So mapping spaces of finite dimensional manifolds and sections of bundles should naturally be this kind of smooth spaces. So there should be a natural operation, which everyone knows here now. It should be a kind of an internal home that produces the right kind of object that you should interpret as a smooth space of a smooth mapping space. Furthermore, we're talking about the infinite jet bundle. Now, jet bundles increase in dimension as you increase the order, so this limit doesn't exist, obviously, in finite dimensional manifolds. So this limit should exist in such a category. And furthermore, it shouldn't just be an abstract infinite limit. It functions out of it, and bundle maps, when you work out enough what they mean in local coordinates and so on, they should recover formulas from the physics, right? Literature. They shouldn't just be an abstract limit in some sense. Furthermore, sections of this infinite jet bundle should exist as a smooth space. The jet prolongation map, which we have used to compose the Lagrangian bundle map earlier, that should be a smooth map between two smooth mapping spaces, so that in the end, such compositions of a bundle map between these two smooth spaces and the jet prolongation should yield a local Lagrangian that is smooth in this. It's a narrow in this category. And furthermore, if integration is also interpreted in this category correctly, that should yield in the end the action functional as an actual map in this category where all the objects that we're talking about exist. Not only that, though, I mean, we have more requirements from this. There should exist a notion of a smooth path in the field space. I also, of course, the real line should be an object in appropriate sense of this category, and such that a smooth one parameter family of fields is recovered by maps in this category as such. In the end, this will say that, well, you can compose one parameter family of fields, a path of fields with the action functional, and in the end you get a map from the real numbers to the real numbers. And we want it to be smooth in the standard sense of smoothness of analysis, so we can take a derivative as we know how to take a derivative. Okay, and then we can prove rigorously that this is this criticality condition is if and only if the Lagrange operator vanishes. Okay. As a bonus, we also want that, we saw that the critical locus was a pullback as a set, an intersection as just a pure set. But, if we're going to work in this generalized category, and we want to, in the end, we want to study actual fields that satisfy the field equations and their geometry, well, then we should demand also that these pullbacks exist. This pullback exists in this category as well. So the on-shell fields, they do have, in a sense, a smooth subspace structure that is usable in the sense that is used in physics again. Of course, all this requires that manifolds, finite dimensional manifolds, should be faithfully embedded as objects in this generalized category. Okay, so this is up to now. This is just smoothness, right, from the description that I've given you that we have required. But it turns out that in physics, I'll gloss over, but some argument. But in physics, there's some arguments that use infinitesimal objects that are not a real line, but there's some sense an infinitesimal line of some order and so on. By truncating Taylor expansions or doing perturbation theory up to some order and so on. You say, you sort of use infinitesimal objects heuristically, but without saying what you're talking about. This is the so-called synthetic reasoning, right? In particular, let's give some examples. In particular, tangent vectors are interpreted as the image of first-order infinitesimal curves, or should be interpreted as the image of first-order infinitesimal curves. I.e., there should be some kind of object rigorously defined, such that maps into a manifold. First of all, the set of maps is equivalent to the set of tangent vectors on M, and furthermore, actually, to the whole smooth thickened structure. But as a motivation, let's stick to that. For instance, let's look at
D1 is a disk, or is it just a line segment?
Yeah, so it's supposed to. Well, it's going to be the following. It's going to be. I'm going to define how and what it's going to be, but it's supposed to be, if this is the real line, and this is the origin, it's supposed to be an infinitesimal line sitting at the origin of order 1, i.e. it should be the space that has functions. It's completely defined as a formal dual, as a spectrum, if you wish, of the algebra given by the dual numbers. Okay, so if you view this as if this epsilon as the linear coordinate, I'll say more about it later, but if this epsilon is supposed to be viewed as a linear coordinate in this would-be space, D1, one-dimensional, this upper index is one-dimensional, and this lower bracket 1 means of order 1, then it says that, well, functions on this would-be space can be at most of order 1. Okay, if you take epsilon squared, it's mapped to 0 automatically. So in this sense, this is a would-be space formally defined as a formal dual of an algebra that has the property that its functions they always see this infinitesimal part of it, if you wish. Now we're talking intuitively, right? This is useful, though. This is very useful, right? In the following reason. So let me just say that, for instance, I told you before that we can define, if you wish, tangent vectors on field spaces, full field spaces, off-shell, we can define them as equivalency classes of smooth paths. This is something we prove. It's just some differential geometry, classical differential geometry that you need to take care of. But this is not a definition. This definition does not work for what physicists use for tangent vectors on the intersection. What they actually use is the algebraic geometry way of defining tangent vectors to detect multiplicities, in the sense that, for instance, if you have this finite dimensional intersection, this parabola x squared, and this real line x equals 0, in the classical way, if you use equivalency classes of paths to define tangent vectors on the intersection, this is vanishing, right? This is just a point. But if you use this kind of definition dually in terms of algebras, this gives you a non-vanishing tangent space at the intersection. To linear order, it just gives you a line, actually. So anyway, so that's the motivation. And the point is that that's what actually people use in physics. They say a tangent vector on field space on the Euler Lagrange locus, vanishing locus, is a field that satisfies the linearized field equations. This is the infinite dimensional analog of what I just said here. Okay. Does that give an idea? Am I answering correctly what you worried about?
It's perfect. Thank you.
Very good. Very good. Yeah. So we should be able to have some object that detects tangent vectors or defines tangent vectors for any kind of, for a manifold, for starters, but also for our theoretic field spaces that we're going to have in this category. Furthermore, people talk about perturbation theory as if it's a restriction to some infinitesimal neighborhood of a point. Think of a Taylor expansion, right? What you do is, well, you take a point and you evaluate all derivatives at that point. So it's as if you formally expand in some neighborhood, some infinitesimal neighborhood around it. It only sees information about what? About the point, its values of all the derivatives in there. So there's in a precise sense that this is a restriction in this setting, in the synthetic differential geometry setting. In a precise sense, there exists an infinitesimal neighborhood of infinite order at the point in the manifold, if you wish, where you just restrict. I mean, strictly restrict your function, and it corresponds exactly to the formal Taylor expansion, and it's related also to jet bundles and so on. Furthermore, one talks about initial data, and these again have a flavor of value along an infinitesimal neighborhood of a submanifold, not of a point. But for instance, if you talk about initial data, let's say of a p plus 1 dimensional manifold along a submanifold of p dimension, what is this? I mean, what are you describing there? You're saying, well, take prescribed field values and values for the derivatives along that submanifold. So again, the same logic of this restriction of a Taylor expansion at a point is the same kind of thing. Synthetically, it's instead of restricting to a point, you restrict to the infinitesimal neighborhood of a point, you're restricting to the infinitesimal neighborhood of a submanifold. This also is a rigorous, it's defined in a rigorous manner. So let's recap. What we want is, we want, furthermore, that such a category of generalized smooth spaces should encode a notion of an infinitesimally thickened structure, making the above heuristics into actual maths. So you're talking about maps in a category, and you restrict and so on, and you recover in the end what you usually write in physics. So that's the motivation up to now. Do we have any questions for up to now, maybe? Or then I can talk some maths.
Oh, it's very nice. Very nice. Thank you. Go on.
Very good. Thank you. Okay, yeah. So let's go straight to the point. So the definition of thick and smooth sets, one should first of all go back to the basics, and one needs to think about principles, about foundations. And one way to interpret, let's say, my way or our way to think about the basic principle of topos theory, which goes back to Grothendieck in algebraic geometry, then Lovir in synthetic differential geometry or logic, then Lurie, infinity version of topoi, and Schreiber, who actually employed this in field theoretic descriptions for higher gauge fields. The basic principle, if you think about it from a sort of philosophical point of view, is to not just start discussing geometry by declaring that you have a set of points plus structure in it, i.e., topological space is a set of points with a topology, or a smooth manifold is a set of points with a smooth manifold structure, i.e. local coverings and blah, blah, blah. But instead, one should think of the geometric spaces in whatever kind of geometric spaces you want to think of. In our case, is smooth and infinitesimal. We should just think of them operationally by giving meaning to what it means to probe this space, to probe it with probes that we know what they mean. I mean, we know with simpler geometrical spaces, smooth spaces, such as manifolds that we know how to handle. We have a notion of what it means to handle manifolds, and infinitesimal objects, which I will define for you. So point being is that we should just drop this sort of handicap of start thinking of geometrical spaces as sets of points plus structure, and instead just thinking of something that is the only thing we can say about it is how is it probed by simpler spaces. For us, it will be smooth manifolds, if you wish, with some infinitesimal thickening by infinitesimal objects, which I will tell you what it is exactly. It will be simple objects. We don't need to talk about complicated stuff here. In particular, what does this mean? Let's be more concrete. This should answer this operational point of view on thinking about geometry. It should just give you answers to when you answer what are the smooth paths in a field space. That should be baked in the definition. And furthermore, what are infinitesimal paths of first order, let's say, i.e. tangent vectors, which we define as a tangent vector space. This should come out from the formalism by definition. I mean, you should set it up properly such that it answers these questions automatically. That's what it means to just change completely how you study geometry. Okay. I'm sure people have other points of views and much more involved in the students on here, but that's my point of view.
It should fall out of your natal lemma.
More or less, in the end, yes, you're right. Yes, I'll get there. Yeah, very good. Yes. Okay, yeah. As a first step for smoothness, one would define a smooth set. Let's not talk about infinitesimals yet, but you would define it as a pre-sheaf, an actual sheaf on the category of manifolds, i.e. just functors from the opposite category of manifolds into set with respect to open coverage. Open coverage mean, well, it's standard coverage. Let me not go into it. Well, I'll get into some intuition of how I think about these things. Of course, you know what sheaves are and formal properties of them, but let me just tell you why this definition just does exactly this kind of thing. Okay? I'll go through it quickly, maybe. So let's go for some intuition. Right, so how do we think about this definition? Let's say I give you a smooth set, i.e. just a functor as such. So for any manifold, sigma, which I think of as a probe, it should give you back a set, right? It's a value, it's a functor value in sets. And how do I think of these? I think of them as, well, it's exactly the collection of smooth sigma-shaped plots in X, period. This is how I think of it in my brain, okay? The definition of what it means to be a smooth, if you're an element in here, you're a smooth sigma-shaped plot in X, in curly X. And I write it just loosely, an element phi sigma of X sigma, which I just say this, I declare this to be the plots of sigma in X. I write it as a would-be arrow. So it's not an arrow yet, but as you know, by your level MIT is an arrow, but anyways, before you get there, you just view, well, it's an element of a set, but I want to view it as plot. So I just say, well, look, I just declare so annotate it as such. Okay, so if I take X of the point, then I think of this as the point plots of X. So I just think of them as being the collection of points in X. I don't know what X is. It might have no points, right? It might be empty, and it's possible, of course. Or if I take the value of X, the functor X on the real line, well, I think of this as the smooth, whatever collection of smooth lines there are in X. Okay, of course, you will have precise description of X, and then this will give you more of an intuition of what this means. But at the abstract level, this is how I think of it. Okay, briefly on morphisms, then, what does this functor do? How do I interpret it? Well, for any map of probes, a smooth map of manifolds, which we know what it means, smoothness in the standard sense of manifolds, well, this is a contravariant functor, so it assigns a map in the opposite direction, and the way you interpret this is as if it just it describes precomposition of plots, of sigma-shaped plots. So if I have a map from sigma prime into sigma, then I get a pullback map, a would-be pullback map from sigma shaped plots in X to sigma prime plots in X. And in this notation of arrows, it's literally doing this kind of job. It's pulling back along this standard smooth map of manifolds, we know what it means, to produce a new smooth plot in X prime. So this is just the definition of a pre-sheaf, right? This is just putting words on what it means to define a pre-sheaf for this specific kind of source, if you want, an interpretation of what it means. Anyways, functoriality makes this description of this arrow description consistent. And further, when we have this sheaf condition, which just says that, well, let me not go into the details. It just means that if you have a covering of an open covering of a manifold by simpler sort of probe manifolds, it says, well, in this simple site, it just says that the pullback, if you take plots, sigma-shaped plots, and you restrict them to each one of the elements of the covering family, then this gives you exactly bijection. So it means that from a smaller plots, smaller sort of plots in your space, you can make up bigger plots. Okay, this gives you a way to glue plots in a intuitive sense. Anyway, so that's all. I mean, you can reinterpret this as all that comes into the formal definition of a sheaf on manifolds, and this is a way to give words on it, heuristics on what it means for us as a smooth set. Okay. All right, let me just skip this very fast. Smooth, well, we have now a category of objects, what we call smooth sets. We know what the natural notion of morphism between sheaves is, pre-sheaves, and this is just natural transformations. But from our perspective of describing plots with sheaves, what does this notion do? Well, it just takes smooth sigma-shaped plots of a smooth set to sigma-shaped plots of another smooth set, and it does so consistently, this is naturality, with respect to pullbacks along maps of manifold and along maps of probes. That's all that natural transformations do in this, or that's all that definition says in this interpretation. Okay, so let me just go on. I don't think this is nothing new to anyone. It's just putting words on stuff people know. So let's talk about infinitesimal probes, right? So now we've talked about manifolds as our site, as our collection of probes, but none of these objects have in any sense an infinitesimal nature. For instance, there is no object D in the category of manifolds with a property that maps of manifolds, of actual smooth maps of manifolds, correspond bijectively into a manifold M, correspond bijectively to tangent vectors on M. There's just no such object in the category of manifolds. So how do we come up with a formal description of would-be infinitesimal spaces as such? Well, we embed the category of manifolds into a bigger category where there is such objects that can be interpreted as infinitesimal spaces. Okay, so here is the crucial proposition, which is just a lemma or Milnor exercise. You can find it in many books, for example, Michor et al. in 93, big book. This is a standard exercise, and what does it say? It says that if you take a functor just take smooth functions on a manifold, so you take any manifold and you send it to its algebra of smooth functions, this defines the actual fully faithful functor inside the category of commutative algebras over the reals, in the opposite category. But now we say, okay, well, there is a certain full subcategory of commutative algebras, opposite, that is literally manifolds. So in this sense, we can sort of enlarge, we can say, okay, let's add some more objects that we can interpret as functions on would-be spaces that are inside and near the image of this functor, okay? In particular, in commutative algebras, there is a nilpotent algebras, okay? These are algebras of these are algebras that we are going to interpret as algebras of functions on would-be infinitesimal geometric spaces, okay? So we're going to take a category, we're going to take specific objects, a specific full subcategory of commutative algebras, which contains manifolds, and the extra stuff are nilpotent algebras or products with manifolds. And then we're going to take the formal dual of that. Okay, that's the whole description. But let's go with an example. As I said before, right? So I want to define a space that would be space D, one-dimensional line of first order, and I want that to be, well, I just define functions, and this would be object to be this algebra, this nilpotent finite-dimensional algebra. Okay, so it's a formal series in this parameter epsilon, this formal variable epsilon, quotiented in the algebra sense by epsilon squared, this relation. So this, well, let me make this extremely simple. As a vector space, this is just the real line plus another copy of the real line with this extra epsilon floating around, and it has an algebra structure such that whenever you take epsilon squared, it gets mapped to 0. Okay, so it encodes precisely the truncation of the Taylor series, if you wish, to first order that physicist. Okay, by Hadamard lemma, this is just an analysis lemma. This is actually the smooth functions on the real line modulo by x squared, the linear actual function x squared squared in the real line. So that means that it's actually a quotient. This algebra is actually a quotient of the functions on the real line. So in the formal dual sense, if I take this to be the algebra of functions on the would-be line, that means if this is a surjective map, let's say an epimorphism, then in the formal dual sense, this would define embedding, literally define the embedding of this infinitesimal line into the real numbers at the origin. Okay, this portion.
Can I ask, what's the intuition there for the Hadamard's lemma?
The point is what it does is the following. It takes any function and the statement is this. I don't know if there's an intuition about it, but the point is that you can write any smooth function as the Taylor expansion up to first order. This is the literal Taylor expansion in real number now in terms of real functions to first order, plus then some smooth function, some uniquely defined smooth function. Okay, which is of order x squared or plus x squared, sorry, and so on.
Right, so you're just going to give the coefficients then, that's the map.
Exactly, yeah. So when you take the quotient by this idea, the ideal generated by x squared, these go away, and this linear x is identified by this with this epsilon. Awesome. So that's it's just a fact. I mean, I'm not sure if there is an intuition. I don't have any intuition about it. It's an analysis fact.
No, yeah, that what you said is what I wanted.
Yeah, very good, very good. Perfect. Yeah. So what I'm saying is I'm defining this infinitesimal line as a formal dual arrow, right, to this a quotient map, taking smooth function in the real line to this algebra that I defined right here, the algebra functions on this. Okay. So once you take that step of just being able to view this algebraic geometry point of view that defines spaces by their space functions, then you can move on and define more spaces as such. So we've defined here the first order one-dimensional line, infinitesimal line. Well, we can define n-dimensional L-order infinitesimal disks exactly the same manner. Let me not go through it. Same kind of quotient business works, and they sit inside the n-dimensional Cartesian spaces, corresponding Cartesian spaces at the origin, canonically, right? And how do I think of them? I think of them as a point with some fuzz around it, some infinitesimal fuzz. If you want to think about it in a heuristic way, sort of in your head, what kind of geometrical objects we're thinking about, it's some point with a fuzz made rigorous in this algebraic sense. Okay? And more generally, even more, we can take formal duals as our spaces of infinitesimal objects. We take formal duals to any kind of Weyl algebras. These are algebras of the form as follows. So these are as vector spaces, they're isomorphic to, well, you have the real numbers plus some finite dimensional nilpotent piece here, nilpotent from the algebra structure point of view. And there is a lemma that says that any such Weyl algebra is actually a quotient of our original infinitesimal disks here. So it's not that far off. It's just dually, meaning it's a further subspace of this infinitesimal points, if you wish. or disks. And that gives you all the kind of infinitesimal spaces that we need for our purposes. You can put more in there. For instance, you can take this to be infinite dimensional if you wish. Oops. It doesn't change much. I mean, there's choices you can make there, but for us, that's enough. It's the simplest amount of infinitesimal objects we can put in there and everything works. And I'll tell you why. Well, let's make it a definition first of all. The category of infinitesimally thickened smooth manifolds is the full subcategory. I denote as thickened manifolds. It's a full subcategory of the opposite category of commutative algebras of the following form. So this I denote the objects as such: RK cross some infinitesimal point, which I think of as some infinitesimal thickening, and it's exactly the formal dual of smooth functions on the original manifold. Oops, here I put RK because I'm going ahead. But any manifold, M, tensor over the reals, it's enough actually, of this kind of this nilpotent algebra. Okay, this nilpotent Weyl algebra. So that's the definition. That's our definition of now thickened smooth manifold. It's completely rigorous definition, and it has a nice interpretation, and we can do computations with it, compute mapping sets between two such things, and so on. For instance, here's a lemma. For any manifold M, the usual manifold, there is a canonical bijection of sets, just a bijection, of the tangent bundle and maps of thickened manifolds from what I just defined to be the infinitesimal interval. This is very standard. I mean, this by definition is the form is dually given by maps in the other direction from the algebra functions on M into this nilpotent algebra. And if you just work out what a map of a commutative algebra does, I mean, just work out this epsilon square demands that the image satisfies some property. You work it out, and it just gives you that it's an evaluation of the function at the point, necessarily by Milnor's exercise, plus a derivation at the point of the function. This is P of f and xp of f. So that's precisely a tangent vector, the information of a tangent vector at that point. So that makes rigorous, completely rigorous, this intuition of having some kind of infinitesimal object that maps out of it detect tangent vectors. Furthermore, this category of thickened manifolds becomes a site under this differentiably good open coverage, which is precisely the coverage that we had for manifolds. But what do? We take open coverages on the finite parts, but then just identity on the products with infinitesimal spaces, i.e. there is no topology to be seen on infinitesimal objects. That's the intuition behind it. And then we have the definition. We just enlarge our definition of a smooth set. So a thickened smooth set now is a sheaf on the category of thickened manifolds with respect to the open coverage and the interpretation that I advocated before, this probe-wise, plot-wise kind of interpretation of such a space still holds. But now we also have infinitesimal objects to talk about. And here's a proposition that we noticed. Well, this for those who have seen before synthetic differential geometry, this definition of thick and smooth sets, I've defined it completely using commutative algebras. For those who have noted, it's actually equivalent to the Cartesian topos from the book in 79. The point is a proof. I don't know. It's just something we noted that the Cartesian site is actually, it has the same objects, I mean, in a precise sense, it has the same objects, but different mapping sets between them. They don't work with commutative algebras over the reals, but with what is called the C infinity algebra. I will not say what it is now. It has a different tensor product, but that reduces to the tensor product over the reals for the specific objects that I've chosen. And furthermore, you can show that home sets between them are exactly in bijection with commutative algebra maps. So actually the sites, the categories are equivalent. So this corollary says that thick and smooth sets, this simplistic model that I've told you, is a well-adapted model for synthetic differential geometry. It satisfies the Koch-Liouville axioms because this topos satisfies them.
That's pretty amazing because like the Coheres topos, that's like the whole subject of that book by Mordic and Reyes, right? Where they have to like construct
Yes.
everything and prove a bunch of like hard
Yes.
stuff.
Yes. So the point is, I think here one should, I mean, there's two sides of this, right? If I wanted to prove the hard stuff, I need to use some properties from C-infinity algebras. I will not go into them, but yeah. But there is some things that you need to do when you work with this kind of this site that require a proof by going through the C-infinity algebra picture. Nevertheless, it seems from one point of view you do need the technology, but from another point of view, you could forget about it in the end. That's what it says. So I've looked at the proof over and over that I've done. So it surprised me in the beginning, but it seems to be, it seems to be fine. So it's not even hard. It's like basic stuff, I think. So, but it doesn't work, right? You see, it only works for this specific topos. I mean, there's many different models. If you read through that book of models of infinitesimal smooth analysis, there is many models, right, for synthetic differential geometry. This is a specific one that makes this work. I mean, if I put more objects in my site, this might not work. It's very specific. That's what I mean. So it's not absurd that they didn't notice. It's just because they worked in such generality with so many sites, and I mean, for a specific site, there is this kind of bijection. It seems to be, maybe, I don't know if it's a coincidence or not, but it's it makes things simpler. At least someone can go into the subject without learning about C-infinity algebras. It seems
right.
For most things, let's say. Right. Yeah. Okay. Yeah. So this satisfying these axioms means, in particular, things that we've seen before. Some of the things. Well, there is a fully faithful embedding of manifolds into this category. Well, this is just Unit dilemma, actually. Furthermore, it preserves pullbacks. This is important. It doesn't preserve pullbacks in the formal dual sense if you map into commutative algebras over the reals, but only in the C-infinity algebras. So, but once you pass to the sheaves over it, then it does. So this is,
Wait, I'm sorry. Say that again.
Yeah, let me skip over it. Actually, it's just details, so it's not too important. Yeah, let me skip over it. Yeah. But in the end, maybe you can ask me about it. Yeah. Okay. So let me make a note here before going further into technical details, that the Unit dilemma, as Professor Nelson indicated, is what makes all of this interpretation work, right? This probe-plot interpretation. Now, what does it say? Right? The Unit dilemma says that, well, take any thick and smooth set, thought of as a space, and I take an element of my site, a sigma, okay? Now, maps of thick and smooth sets between the embedded sigma and X, these are actual maps now in some category, some arrows. These are in canonical bijection with the evaluation of the sheaf on sigma. So actual plots. So it's a sort of, Unit dilemma says that you sort of bootstrap what do you mean by probing your would-be space. So pre-sheaves, in general, sheaves, if you wish, the Unit dilemma guarantees this interpretation works. It's exactly what makes this work. Yeah, exactly. Yeah, so let me just say we can simplify the site further. The reason being is that, well, any sigma cross D has a Cartesian open cover with charts covering our manifold. And thickened Cartesian spaces, which just include Cartesian spaces cross infinitesimal spaces, they sit as a full subcategory. And the sheaf condition then implies the equivalence of the categories of sheaves over these. So intuitively, well, we can define as a equivalent category that thick and smooth sets are just sheaves over thickened Cartesian spaces. So we can even, what it means to probe a space by an arbitrary manifold, we can recover that by probing just with Cartesian spaces and thickened Cartesian spaces. So this is, I think, due to Schreiber originally, this small observation, but it's intuitively, it's nice from the point of view of probing and so on, because it says, well, you only need actually the simplest objects we have for describing smoothness in real analysis, not manifolds. We don't need manifolds, we just need Cartesian spaces. And the infinitesimal objects, we only need the simplest ones, it seems, for physics, at least applications. Okay, examples, smooth manifolds and their tangent bundles. As I said, well, the Unit embedding not only does it embed any thickened manifold into thickened smooth sets, but also any unthickened one, because this canonically embed into thickened manifolds. So this is fully faithful. And as being a sheaf category, a pre-sheaf category, it has an internal home functor, which yields a notion of thickened smooth mapping spaces. For any two thickened smooth sets, I produce another thickened smooth set such that the points of it, the actual points, right, in our interpretation of points in our thick and smooth manifold, what are they? Are just the maps between them, right? By definition of the internal home. So it makes sense. It's as a set, at the set theoretic level, it recovers the set of maps between it, but now it also has whatever you mean smooth paths to be, or infinitesimal shaped plots. Okay, and here's a proposition now you can prove in this category. So, for instance, this is in the original Moredig and Reyes 91, this big book. We reproduce it in the simpler site. So this says that the Lloreda embedding of the traditional smooth manifold tangent bundle is isomorphic as a thick and smooth set. So including this extra structure of smoothness and infinitesimal structure to this internal home object, okay? And point being, right, so if you apply this on a point plot, this recovers the original argument, this lemma that I told you above, but now it also says that it preserves the smooth, it agrees as a smooth, thick and smooth set as well, okay? Notice this is a good stepping point now to define tangent bundles for any smooth set. This left-hand side has embedded something from standard differential geometry, fundamental differential geometry, some construction, and it's identified with a natural categorical construction in this sheaf category. And well, we call this, we make this into a definition, and we call it the synthetic tangent bundle, being the functor which just takes the mapping space of any x, of any thick and smooth set x, and it yields the mapping space of with source the infinitesimal interval first order. Okay. Now we apply this. We apply this to our field theoretic spaces, and we see that it recovers what we want. Okay, and it's not too hard actually. Okay, so let's go back to physics. Okay, let's start. Let's start with the case of thick and smooth sets of fields, right? So let's take a field bundle that I advocated earlier. Let's just take the trivial one for a moment. This is M cross N. So the trivial fiber bundle with fiber N over a manifold space-time manifold M. Then the set of sections, i.e. fields on the space-time would be just smooth valued functions from N to N. So maps of manifolds from N to N, okay? But now we can embed into our thick and smooth sets, and we can take the internal home, which gives a natural smooth set structure, thick and smooth set structure. In particular, this has plots, if you wish. If you evaluate it on particular probes, it tells you exactly, we just work out what this definition is. It just tells you that what are smoothly RK parametrized families of fields, right? Or paths, if you want, if you put this to one. Well, these are, it just tells you what they are. Just the definition spits it out. And it is what is used in physics. It's exactly what they mean when they say by one parameter family of smooth fields. This definition just yields it out. But it also tells you, you can calculate what it means to, well, what is the infinitesimal D-shaped plot in this field space. Okay, for instance, you can apply it for tangent vectors. But first of all, as I said, for curves, it gives you exactly what physicists have been using as a notion of a smooth one-parameter family of fields. Just take the product here inside the source with the source manifold, and why? Well, I don't know why they do it, but from a mathematical point of view, this gives me a justification. It comes categorically from this internal home. It's very natural. Okay, so this tells you what a smooth path in our field space is, and it's exactly recovering what's used in physics. While also then, well, we can apply this F, this internal home, and apply it to the infinitesimal interval, and well, this should give us tangent vectors, and it does in the sense of physics. Well, here's a small lemma. If you apply the synthetic tangent bundle factor on a field space, i.e. T on this mapping space here, well, this is canonically isomorphic to this mapping space M, valued in the tangent bundle of N. And the proof is just using adjunction properties and internal home properties. So this is the left-hand side. Let's just go through it, right? This is isomorphic by the internal home property to D cross M, comma N. And then by the internal home property and just switching this product here, symmetry, then this is M, internal home M valued in the internal home D into N. But we've already proven, well, we've already said that there is a canonical unification of this with Tn. So it recovers exactly, this is what physicists mean by tangent vectors on a mapping space from N to N. This is what they use. Okay, but now we just talked about the trivial fiber bundle. Well, we can just, it's not hard to go to an arbitrary fiber bundle. You take an arbitrary fiber bundle. Let me just tell you what the space of sections is. Plot-wise, it means, well, what you do is, well, you take an RK cross D parameterized section. Well, it's literally an RK parameterized section, or more formal if you want, from the categorical point of view. The set of sections of a fiber bundle is given by this diagram computed in set. But now we just compute it in thick and smooth sets, and it gives us exactly, it recovers exactly this information. You just compute the pullback diagram. You do it object-wise, right? It's a sheaf. Okay, and here's a proposition now generalizing the previous mapping space construction. It says, well, take the synthetic tangent bundle of any field space, right? This is it, with the above definition. And this is canonically isomorphic to the smooth set of sections of the vertical fiber bundle, okay? So let me just say again, this is what is assumed in physics heuristically. Now this comes out very nicely. And the proof is, well, you just take the internal home with the infinitesimal line here, you apply it on this diagram, and because it's a right adjoint, and it commutes with limits. So anyways, in the internal home, and you just compute out categorically if you wish, and then identify something plot-wise in the end to make contact with the traditional physics. But yeah, that's it. I mean, just comes out. Okay, so here's a question then. We've recovered some tangent bundles and so on. We have notions of smooth paths. Now the question is, for this variational discussion that I told you about earlier, well, do local Lagrangians, in the traditional sense, do they define maps in thick and smooth sets? I think Emilio pointed this out. This is what we want in the end. All these arrows that I wrote, we want them in the end to define not just maps of sets, but maps of thick and smooth sets. Now I have defined what is the thick and smooth set of fields, and the thick and smooth set of top forms is just some sections of another bundle. So I want a local Lagrangian, which usually people write as like this kind of coordinate-wise description. I want it to canonically define a map of thick and smooth sets with the correct properties. And the answer, of course, is yes. And shortly, it's by working and first embedding to thick and smooth sets and working directly in there. So,
are you not going to run into a problem though, because you're saying top forms, but there's no dimension on?
No, that's right. So M here, no, M is a fixed. It is an actual manifold. It's an actual one. It's a space-time. Yeah. So I'm not going now on infinite dimensional space-times. My spaces of fields are infinite dimensional in that sense, but the actual space-time is always finite dimensional, right? Whatever dimension, but a normal manifold.
So you fixed M, you fixed the bundle,
yes.
Then you have a sheaf of sections. Okay, thanks.
Yes, correct. Very good. Sheaf in two ways, right? It's actually, now that you say that, it's a sheaf on M, if you want to be more precise, in the topological sense, and it's also a sheaf in this thick and smooth set.
Yeah, that's what confused me. Thanks.
Yeah, very good. Yeah, so how do you do this? Well, you embed all your, first of all, your finite jet bundles. These are finite dimensional manifold. You can embed them, unit dilemma, take the limit in here, you get your infinite jet bundle, and you check, well, you have maps, well, it becomes a bundle over M. So you have sections of this in this thick and smooth set way of defining them, fine. And here's the lemma, well, the jet prolongation defines a map of thick and smooth sets as such, okay? So let me just skip it, but, well, yeah, for the interest, it's just a calculation using the limit property and the particular description, coordinate-wise description, if you wish, of each finite order jet prolongation maps. So it works, plot-wise, if you wish. And it is what you expect in the end, right? In the end, what you do is you take the coordinates on the infinite jet bundle, there would be coordinate functions on it, you just send them to the value of all the derivatives. But now these are parametrized by this extra plot-wise parameter space. Anyways, we will not confuse you, but it exists as a map in the formal sense. Then, turns out that fundamental Lagrangians in physics are actually of finite order. So they are not of, they are pullbacks from a finite jet bundle. That means in this embedded picture, well, you just embed this whole picture of a finite order Lagrangian as a bundle map. You pull it back up, and it defines a map under the Yoneda embedding inside thick and smooth sets. So then you can compose them with a infinite jet prolongation, and it does give you a map in thick and smooth sets. And lastly, well, the integration also can be extended to canonically to a map of thick and smooth sets, right? It's something trivial. You take any parameterized form on M, and what do? Well, you have a parameter here, which is of, so you take top forms on M, projective tensor products, so this is the only thing that you have to be careful of, with C infinity of RK, tensor over R if you wish, with some this finite dimensional algebra. And you integrate over M, keeping constant these guys, and then you just sum over again this extra formal variables. So it's an easy thing to write down. Here's an aside, which I should probably skip for the sake of time, but the point of this aside is that there is an actual abstract construction called the synthetic jet bundle construction, and this does recover this limit of embedded finite dimensional jet bundles. So, and at the point-wise level, at the point plots, this just tell you this infinite jet bundle, synthetic jet bundle. What it does is it just gives you the set of sections over the infinitesimal neighborhood at a point, and this infinitesimal neighborhood at a point is just defined to be all plots in your smooth set, thick and smooth sets, that once restricted along the finite direction, they actually factor through the point. So I'm just saying that, well, how would you think, let me just tell you this intuitively, how would you define an infinitesimal thick and smooth set while all you can say about it is what are its plots, okay? Well, I can say, I give you a thick and smooth set and a point in it. Well, what is the infinitesimal neighborhood around it? Well, it is a space that can only detect infinitesimal plots, but not any finite ones. This is exactly what this definition does. And you can be more categorical about it. There is some adjunctions and so on that you can form in there anyways. But this is intuitively what it does. It is the space that only sees the infinitesimal plots around that point, but not the finite ones. And actually, if you work this out, it gives you the correct definition. Anyways, that's all. I'm not going to go into details. To recap, right? Composing maps of thick and smooth sets. We have a Lagrangian and the infinite jet prolongation, and we get a map of thick and smooth sets into top forms. Then we can integrate. Oops, I'm very sorry. What happened? Oops. Yeah. Oop. Yeah. Sorry. And do that. Good. Then we can integrate with the integration. We can compose with integration, and we get a map from field space into the real line. Okay. In particular, we can apply. We can check the value of this map on smooth R1 plots. Okay, so on smooth paths. So on smooth paths, this gives precisely a map between, well, look, it's a real numbers into F, curly F by the Yoneda lemma, and then composed by S, and you get a map from the real numbers to the real numbers. And then you can just take the derivative. Again, Yoneda embedding comes in all the time, right? You go back and forth from manifolds viewed as thick and smooth sets and as just manifolds. Here's a proposition. Here's in the smooth setting. Here's a proposition that makes this work. For any local action, well, you can define that any point plot of the field space is a critical point if and only if the Lagrangian equations are satisfied. But not only that, an arbitrary RK parameterized plot is critical in this sense, if and only if the corresponding Lagrange operator vanishes on this plot. So this says that the critical plots defined in this sense form a smooth set. A priori, for an arbitrary smooth set, this kind of construction here is not natural, it's not categorical, right? But this proposition says that it is actually defining a pullback construction. Okay, so this is what the content of the proposition is. So what physicists have been doing is actually functorial in a sense for this kind of specific local Lagrangians. So this we proved in smooth sets, and then in the following paper we should extend it to infinitesimal plots as well. I mean, it's done. It's minor things. It's some lifting of plots. So in the end, this will say to come. This will say that not only one can view a variational principle in smooth sets, but also in thickened smooth sets, and it yields a pullback of thickened smooth sets. So it yields that the on-shell field space is a pullback of smooth sets, thickened smooth sets. So it has an infinitesimal structure as well. Here's a corollary of this. The corollary is that the on-shell synthetic tangent bundle construction then recovers what physicists have been calling the tangent bundle of fields satisfying the Lagrange equations, i.e. they call them Jacobi fields on space-time. These are solutions to the linearized Lagrange equations. You can work this out. You apply again the synthetic tangent bundle functor to this diagram, commute with limits, you work out some extra, you work it out, and you see in the end that it comes out exactly as you wish. Okay. So this, for instance, this I haven't seen anywhere else. How would you do this? Otherwise, I don't know. Here is a remark again. This is not the same. This tangent bundle construction is not the same as taking equivalency classes of curves in here. And this is the example I told you in the beginning. If you take equivalency classes definitions as a tangent bundle for this intersection, it gives you a point. But the synthetic one gives you the real line. Same thing occurs, of course, in the infinite dimensional setting, right? Okay. Very good. So let me just now run through some list of words that you might have heard, and I'll just tell you now that all of this becomes rigorous in here, and then you can ask me more questions, or maybe I'll give an outlook for further parts in this series. Unless there is questions already. Okay, good. I hope I haven't lost everyone. Okay, let's see. Okay, so here's a list of other concepts. One talks about symmetries of field spaces. So you want automorphisms or diffeomorphisms or automorphisms of your field space. These are given automatically now. We know what it is. I mean, there's maps in this category that are invertible. We have tangent bundles. We can define vector fields as sections of these tangent bundles on field spaces. These recover exactly, if factored through the infinite bundle, they recover exactly what people have been using in the literature in coordinate formulas. So one can talk about finite or infinitesimal local symmetries of any Lagrangian field theory. Or you can talk about any initial data smooth set then. I mean, the initial data now actually defines a thickened smooth set, not just a set. And why is this important? This is important because you want to talk about Cauchy surfaces in physics. Cauchy surfaces, by definition, okay, I haven't told you what the initial data is exactly, but anyways, sort of glanced through it. But a Cauchy surface is some submanifold, finite dimensional submanifold of space-time of codimension 1, such that the restriction of fields along this submanifold yields a bijection, or not bijection, but it's now an isomorphism of thick and smooth sets in our setting. Okay, so this doesn't just give you initial data, but it tells you that this restriction map, if it is a Cauchy surface, it actually preserves also infinitesimal structure and smooth structure. So now P-form local currents, you might have heard of currents. These are just maps of value in P-forms instead of top forms like the Lagrangian out of the field space. Charges, then you integrate along some manifolds, you get charges or on-shell conserved ones, which are the ones restricted along this critical locus. Then Noether's first and second theorem, they're about actually infinitesimal local symmetries. They become rigorous in these infinite dimensional spaces. Notions, as I sort of glanced, hinted very quickly, a notion of an infinitesimal neighborhood around a point, around the configuration in field space, they exist abstractly. Okay, I can just define what it means abstractly. And then perturbation theory in this infinite dimensional setting should be, the proof now becomes more difficult, but it should be in this infinite dimensional setting, just the restriction, given by the corresponding restriction of the Lagrange. Now there is an issue with recovering the formulas from physics. I mean, it might sound completely plausible, but since we're trying to recover everything as done in physics from this rigorous perspective, I haven't been able to do it yet for the infinite dimensional setting. But if you take field theory over a point for the finite dimensional setting, you can prove that this abstract definition of an infinitesimal neighborhood and the restriction of a function along it corresponds exactly to the Taylor expansion. So it works. I mean, it should work for the infinite dimensional setting as well. What else? Yeah. So from a formal perspective, there exists classifying spaces of forms in this category. These do not exist in the smooth set category. They only exist in the thickened smooth set category. This is something important that I think many people they want to define forms for an infinite dimensional space in the sheaf theoretic language, and maybe they work in diffeological spaces or smooth sets, and they just take maps into some sheaf of forms plotwise as a definition. But this doesn't have to do anything with any tangent vectors in the smooth set setting. Only in the thickened smooth set setting, this becomes an actual classifier for maps out of a tangent bundle. Okay, fiberwise linear. Okay, yeah. And then more stuff. You might have heard the variational bicomplex. Now it's recovered using, or the local bicomplex by Zuckerman and Lin-Fried. It's recovered by using synthetic tangent bundles, the infinite jet bundle, synthetic push forwards, and everything synthetic. If you work out with it enough, it recovers exactly. It defines it rigorously, and it recovers exactly the formulas in physics. So everything, as far as I understand, in classical physics, can be made rigorous here. In the phase space, I'll just skip through it. I mean, if you hear the words covariant phase space or phase space and non-covariant phase space, all of this as well becomes rigorous here. I just skip through it. Let me just give you an outlook and wrap up. If that's fine.
I think it's an idea just to go through the slides, and when people are watching it on the video, they can stop the slides.
Yeah, of course. Yeah, very good. Yeah, let me not go into it, but as I said before, for the phase space, the point is that the on-shell space of fields, now that we've identified as this intersection, this pullback diagram in thick and smooth sets, is not just a thick and smooth set, but it has an extra naturally induced structure for local Lagrangians, which is a local symplectic, pre-symplectic current. This induces Hamiltonian currents, Poisson brackets. You can do transgressions, and all of these are maps in thick and smooth sets. That's the idea here. Yeah, and this is the construction. These slides show the construction, and then in the end, this defines the covariant phase, what's called the covariant phase space. Covariant in the sense that you have not used any splitting of your space-time into space and time, and not initial data has been chosen yet. But if you do have a Cauchy surface, then transferring along this Cauchy restriction that I mentioned before yields a non-covariant phase space. So this become rigorous here, definitions. Okay, yeah, and you can check in examples. It does what you expect. Very good. Okay, so here is an outlook on the series. You might have heard about fermions in physics, and it's a big fuss. But the fermions exist; they are real. I mean, they enter mathematically, even at the classical description, even though they have no classical interpretation in terms of observables. When you want to quantize a theory, when you do want to do quantum electrodynamics or whatever, then you need to write down an action function. The point is that people write expressions as such, and this is a simplified form of the standard model on the real line. Let's say this is for a fermion psi. You see, the point is, what is this psi? I mean, as a mathematician, what would you say this is mathematically? I mean, if this is just a function on the real line, then this is just you integrate by parts. This is a top form. This is a trivial theory. So it is not that. Then you say, well, maybe it's a fermion. So maybe it is not a map of between the real line and a vector space, but it's actually from the real line to a node copy of a vector space as a map of supermanifolds. But again, if you calculate what this is, this set of maps, this is zero. This is nothing. Because one is even, the other is odd. So there's just work the opposite algebra way. It just gives you a vanishing set. The point is, what is this symbol that people write all the time? Okay, and what is it? And the answer is that it's an arbitrary RPQ plot of this smooth, thickened supermapping space. So you need to further extend your site to include odd, um, Cartesian spaces. Okay, I will not go into it, but that's the whole point. Once you enlarge it, then these objects, these weird formulas, they also become rigorous. I mean, they become an arrow in a category, and you can work with them completely rigorous. You have an interpretation, a level-wise interpretation. Anyways, you get jet bundles of odd bundles, local fermionic, bosonic Lagrangians, currents, blah blah blah. They extend, and the point being is that this includes the standard models. It's not just this is actual physics. And it seems necessary, right? Otherwise, if you don't do that, then these symbols they don't have any mathematical meaning. I mean, they would vanish otherwise.
Mathematically, usually say something that the difference between a fermion and a boson is how they react in terms of the tensor product. In other words,
Yes.
whether so, but that's totally not here.
Yeah. So people in manipulations, you would say, you see, these are, you write psi1, psi2 equals minus psi2, psi1, right? I mean,
Right.
You have this
That's
odd.
for right, as opposed to a boson where it would be equal.
Exactly, yes. And the point is that if I write a Lagrangian here with two of the same size, and I integrate by parts as such, is a first order, then it becomes a total derivative because psi squared is zero, because psi is equals minus psi. And that would be just a trivial Lagrangian, but it is not physically. So that's the point. The point is, how do you both incorporate this anti-commutation law, but also in a non-trivial manner? Why is the formula non-trivial? That's exactly the point. Yeah. So you
But
incorporate.
you don't have the same problem with bosons.
No. Bosons are already in thickened smooth sets, and it's fine. Yeah, you don't have such a problem yet. Yeah, that's right. Yeah, and let me just end up with a further part in the series. This is about now going into actual higher geometry. Finally, this is about talking about gauge fields. So if I want to talk about electromagnetism with non-trivial topological sectors and so on, well, non-perturbatively meaning, I need to enrich the site with further probes, high simplices. So in the end, my functors will be valued not in sets, but they will actually be valued in simplicial kind complexes and so on, simplicial sets. I.e., we want to talk about thickened, super smooth infinity groupoids, and this will encode this what is called in physics gauge transformations, i.e., equivalencies, ways of viewing as field configurations as equivalent. This is a hallmark of gauge fields, and then higher and morphisms between morphisms and so on. But anyways, this is further along the road, and one further step is to go derived, but okay, let's not.
Okay, let's stop here. It's
Yeah.
an hour and a half. Anyway,
Yes.
it's very nice. Very wow, a whole world. Any questions? Matthew, fire away.
Thanks. This was amazing. I
Thank you.
have a couple of like vague questions. Okay, like one, all right, so two vague questions. One, you mentioned earlier, when you had a picture of like the line with the parabola that you got the sort of the correct intersection, like you got the correct tangent space when you took the intersection of smooth thickened sets, but you didn't do anything derived.
Yeah.
So
That's.
always work without having to do derived.
I mean, not yet, right? Depends on the purposes. So thick and smooth sets, they detect multiplicities. I get that the tangent space is not, like it touches twice, right? It's x
Right.
squared. Yeah. So I detect multiplicities, but then for other purposes, for derived is better. And I'm not an expert in that. But for the purposes of at this stage, for these purposes, thick and smooth sets are over enough. Yeah, they're completely recovering everything you expect. Yeah, but you
Got
are right. Yeah. You need to, for quantization. This if you've heard the words BP quantization, if you want to
Yeah.
try to do something like that non-perturbatively, you would want to go derived then. Yeah. So that's right.
Gotcha. Okay. And then my other question is like, so I'm actually learning about renormalization right now. And in renormalization, when you renormalize, you end up with a lot with sort of these effective interactions that are not local
Yeah.
functional, but are like maybe approximately local. is there any framework? Is there any framework for dealing with these non-local functionals in this language?
So I have not. Oh, what happened now? Now I have an echo. Where is the echo from now? Is it? I think it's from you. Maybe. Can you mute after you speak, please?
Somebody needs to mute them. Here, I'll mute.
No, Matthew, you mute. Okay, go.
Yeah. Okay. Good.
No, that doesn't help. Maybe I'll mute.
That's crazy now. Okay. What about now? Okay, good. It was me. Sorry. Okay, good. Yeah. So I didn't think too much about it, but my guess is that these non-local Lagrangians, these are multi-local in a sense, right? So they factor through. I think I have a remark in the first paper we made. There is a certain class of Lagrangians that are non-local in the strict sense, but are close. And I think those should fall into that category. And these would define, again, smooth maps of smooth sets or thickened smooth sets. I'm pretty sure. I've not done it. We didn't, I mean, there was enough things to do already. But I think, I would be very surprised if it just didn't fall into place. I mean,
Yeah. I was just wondering if any work had been done in formulating renormalization in this language.
No, we haven't done anything. Not to be honest. No, we didn't even think about it. Yeah, but but it's definitely interesting, right? I mean, this is the setting where it should be. I think. Rigorously formalized. Yeah. That's the end goal, very long term, is to do everything rigorously. But but everything takes time. So.
Yeah. Really cool stuff. Thanks.
Yeah, thank you.
Yeah, I have a couple questions. I hope that's all right.
Of course.
So let me get this straight. So for the first paper, basically, you've rigorously done like classical field theory. And then if you want to include fermions, then you have to go to this like other site of super thickened Cartesian spaces.
Correct.
And then what was the next one that you need with derived?
You don't need to derive yet, but to do gauge fields, to just describe the field spaces of gauge fields, right? So groupoids, right? I mean, groupoids don't. So you want to describe. Let's step back one moment. So if you talk about Yang-Mills theory or connections on a principal bundle, if you actually talk non-perturbatively, this has different topological sectors. And these have automorphisms, right? The automorphisms of the corresponding principal bundles where the connections live on. Okay, so these define groupoids. They don't define sets. So if you actually want to talk about the smooth and thickened structure of them, you don't want it to be a smooth, thickened set, but you want to include this groupoid structure as well. So you need to be valuing groupoids. And then if you want to go higher gauge fields, then you want to do infinity groupoids. So that's the idea, yeah. And then if you want to go, so that what does that do in this? So you enrich the site further in an appropriate sense, and then you're valued into simplicial sets or Kant complexes. Okay, but you can view it as being starting from thick and super Cartesian spaces valued into simplicial sets. This would define what is thick and smooth. Super smooth infinity groupoids. Okay, and then you get better quotients co-limits if you want here. Then, if you want to do better intersection theory, then you want to do derived. And then what you do is, then you go back to your site and you make that derived. So you would say instead something like, or some equivalent, or it's there's details and it's complicated, but I would say something like DG thick and super Cartesian spaces should be enough. Positive.
So instead of taking R algebras, you're going to take
yes.
R quotient complexes.
Roughly, right? There is many details and adjectives you can put there, and you should or not, but roughly yes. And this should be the setting where you can make definition. There's attempts already. There is a paper by Alfonsi 2023 that makes an attempt into defining such, but this is not the site they choose. It's different, but it's more complicated, and I have not yet been able to see if it connects to the physics directly. It works as abstractly, but I'm not sure. Yeah, maybe does. And I think there were announcements by Cartesian and William as well that they were working on this. this derives higher smooth geometry where you can make BV, BRST non-perturbatively rigorous. But I haven't seen yet, as far as I know, a paper or something yet. It's not like we have it ready either, but I'm just saying it's hard stuff and this takes time. So it's completely, I understand why, now that I've been working on it for a while, I understand why it's hard to do. Yeah, it's difficult stuff.
Right. Like the abstract stuff has already been worked out, but the hard part is checking that it actually gives you physics, right?
Yeah, correct. Exactly. Yeah, I agree. Yeah. I mean, yeah, there is details again that you need to do abstractly, but that are specific to these constructions and so on. But then, yeah, getting out these, actual formulas for fees, it's not easy. It's like takes time and hard work, and sometimes it doesn't work, right? I have many occasions where you need to be careful. Many abstract constructions then just don't give you the correct thing, so you need to be careful what you do. For instance, let me not go into it. Yeah.
So I don't know any physics, so I apologize. But when people say quantum field theory, do you need to go to the level that you're on right now to talk about quantum field theory?
No, I mean, when people talk about quantum field theory, first of all they talk about usually about perturbative quantum field theory, and this is not, yeah. So first of all, they're usually not talking about this thing either, and they're talking about perturbative formulations of BRST as well. So this is in the end, it ends up being renormalization plus Feynman diagram expansions. So you don't need to know this stuff, but the ideal goal would be that if you actually want to properly formulate non-perturbative quantum field theory, then you would first need to, we assume, you would first need to formulate classical field theory rigorously. So you will need to go step by step. That's the idea. So that's how a mathematician would think, right? I think. So, that's the idea and that's the end goal, and that's what we're trying, along with other projects on the side. But yeah, you don't need, if you want to study, not only you don't need it, no book in traditional perturbative quantum field theory would ever say any words I said today. I think, well, I mean, the physics words they would say, but any of the math words they would never mention. So it might be also
perturbative quantum field theory is like almost like a caricature, right? It's like they cut off at a certain level and they just do like.
Yeah, so one way to think about it is that first of all, there's perturbative in two senses. There is perturbative classically, this is a step you also do in quantum field theory, right? So what you do is you fix a fixed solution, classical solution, and then you expand your quantum fields around it or something along that manner. That would correspond in our language to, hopefully, to restricting to the infinitesimal neighborhood of that field. So at the classical level, this would be in this setting, rigorously made. But then in quantum field theory, there's a second perturbation level where you do these expansions in the H bar. So this corresponds to the Feynman diagram expansion, and then you do another cutoff because this expansion, both of them are formal expansions. There's no guaranteed convergence. Actually, it's probably non-convergent. So in many cases, most cases. So yeah, so I don't know. I mean, yeah, I cannot say anything about the quantum rigorously, to be honest. Non-perturbatively or perturbatively, there is work by. There's many ones that I forget their names. So let me not say some and not others. There's many trying to make perturbative or have already made perturbative quantum field theory rigorous. So yeah.
Okay, my next question is, so you have thickened Cartesian spaces or the thickened smooth sets, and so I want to consider like concrete sheaves on this, right? So these would be like thickened diffeological spaces or something, and then you get a notion of a tangent bundle by just taking internal Hom with the derived with the infinitesimals, right? But there's
Yes.
already a definition of tangent bundles in diffeological spaces, and so I wonder, is this tangent bundle and the one that's already
Yeah,
defined?
they do not agree, right? I think they do not agree. I think that, so Christian Bloman, I hope I say his name right. He has some work on this where he tries he has some notes that he tries to do this classical field theory in diffeological spaces, but then he runs into this kind of issues where the tangent bundle, the diffeological tangent bundle, is not the one specifically for, if you want, for the on-shell field space is definitely not the correct one. Now, I don't know, maybe for the off-shell field space, it agrees, because there you have other definitions agreeing as well, like just taking equivalency classes of curves that recovers the same definition for the off-shell field space. So in general, I would say they don't agree. Yeah. But also, when you say concrete thick and smooth sets, it should be diffeological spaces cross. But would it be exactly that? Maybe there is something else to check there as well. It's a fair assumption, but maybe I'm not sure if it's exactly that. Yeah.
But the space
smooth sets, it's true. In smooth sets, of course, the concrete smooth sets are just diffeological spaces. But then I'm not sure if they, making this step then to just saying, well, what is it exactly? It's just diffeological spaces cross infinitesimal objects, or what exactly did you mean? I'm not sure.
Oh, I didn't mean anything.
Okay.
I have no idea. I was just thinking like, I'm just curious because you can embed diffeological spaces into the thick and smooth sets and then take that tangent bundle, you can compare them. That's what I was saying.
Yeah. So how do you embed the diffeological spaces into thick and smooth sets? So there is some kind of extension business you do there, okay? And it turns out that I in the beginning I thought, well, everything we need to do to pass from classical field theory in smooth sets to thick and smooth sets is just take this kind of, there's some adjunctions and then some kind of extension you can take for smooth sets into thick and smooth sets. Now, I don't remember the details, but I remember spending like a month or two just checking whether trivial things hold, like a mapping space, right? You form a mapping space in smooth sets and then you take the embedding along this kind of extension. This does not necessarily coincide with a mapping space formed by first embedding the two manifolds, and you have all these issues there. You see, so you cannot, and it has been assumed by so my collaborator here, whom I've learned a lot, by Urs Schreiber. I think we have this discussion a lot once in a while back then when I was doing this stuff, because he assumed and I assumed as well that you just do the abstract thing and you get out what you want, but it didn't work. Mapping spaces didn't work. Other things didn't work. There's other things that didn't work as well. So
there's something really non-trivial going on then. That's
cool. Classifying spaces of differential forms that didn't seem to work either, unless I wasn't able to prove anything, but I find it unlikely. So many things just didn't seem to come out as one would expect. Perhaps I missed something, but I highly doubt it. It just seemed like it just didn't seem right. It's been 2 years since I saw that specific problem, but that was a specific occasion where an abstract construction just didn't. You should first pass to your good category, then you do the categorical constructions, rather than working with sheaves on this side and sheaves on the enlarged side and then embedding and so on. And it's not the same. I don't think they commute, for many constructions.
It makes me wonder if studying concrete sheaves on the thickened, the thickened smooth, the concrete thick and smooth sets, I wonder if that would give you like a very different flavor of diffeological spaces, and I wonder how the theory would change. But
good question. And there might be literature on it, to be honest. I'm not completely sure. So maybe more the Reyes, they say something about concrete sheaves there, in their model. Maybe. I'm not sure. But it seems like a natural question. That's what I mean. So perhaps you can find something on it. I don't have much to say about it. Sorry.
All right. Less technical question. Have you talked to like other physicists about this kind of work? Like I know Hisham and Urs are physicists, but like have you talked to people who like just do like hardcore physics? Have they had any kind of reaction to this work?
I went to a conference. I tried to present to physicists very much more basic stuff, right? Just what can you do with probing cases and plots. I tried to be very simple, just this kind of. I just explained what is this formula, what do you mean mathematically. The very physicsy people, I think they just don't care. Or they I don't know, they don't see any benefit into it. Let's say I'm not judging it. It's just from their perspective, for their goals, they don't see any benefit to further delving into what you mean by the formulas or something. So, there were a couple.
I once spoke to a computer scientist and I explained to him something what I did, and he said, "Oh, well, that's just math." And I said, "Well, leave out the word just." And he said, "No, it's just math."
Yeah, exactly. Yeah, maybe that's how they view it as well. So, yeah.
Okay. Can I ask one quick question? The Noether theorem 1 and 2. The results would be some type of constant function. In other words, some type of invariant statement.
Yeah, so it's conserved current. So it yields, where are we? Are we here? Yeah, so it yields this kind of stuff. It's to any kind of local symmetry, to any vector field, in this thick and smooth set sense, local vector field that preserves the Lagrangian in a precise sense, all defined in these papers. There corresponds some p-form current, such a map here,
Right.
that is closed, that is that satisfies delta m p0 along the differential of
Okay.
space-time. And then
Right.
this translates to, if you take two slices and you integrate, then it's preserved along a slicing, along time direction, so on, if you wish.
And so it's a purely mathematical theorem.
Yeah, fully mathematical, yeah. No, completely rigorous. But this, okay, it's, one would argue it's already rigorous from the time of Noether, right? It's just that mathematics were at a different level of rigor then. So we just made it. Yeah, we just.
She had no. She had no. But yeah, she had no problem with.
Exactly.
Right. Anyways, thank you very much. Fascinating stuff. Fascinating.
Yeah.
You got to come back and give us part 2, 3, 4, and 5, but it's going to take your time. But whenever you're ready, we're ready to listen.
For sure. Thank you very much, and thank you for the invitation and for.
Anyways, thank you very much.
Do you mind if I email you with questions? Because right now I'm working through the work of Costello and Gwilliam on renormalization and BV quantization, factorization algebras, and all that.
Sure, you can email me. Yeah, but just bear in mind, I spent also like a couple of years studying that, 1 year or more, like 3 years ago. I haven't used it at all up to now. I'm doing different stuff. So, but bear in mind, I have a lot of questions as well on that book. If you want to ask me about that book, I can also ask you about that book. So.
Yeah, I know it's hard. Thanks.
Anyways, thank you very much. Okay.
Yes.